Hi, and welcome back. This is the second tutorial video for this term. We'll be continuing to learn about particle motion. Before we dive into the tutorial problems, I'd like to give my explanation for the right-hand rule. Many of you indicated that this is a confusing concept for you, so I hope that my explanation is clear and easy to remember. The right-hand rule is a convention for figuring out which direction a vector is supposed to point, and it allows us to answer two important questions. The first is, how do we express a rotation as a vector? Angular positions, rotation rates, and rotational accelerations are very important in dynamics, and they can all be represented as a vector quantity. The second question asks, how can we know the correct direction for a cross product? Cross products will become important in later concepts. If you Google the right-hand rule, you will find many pictures where the thumb, index finger, and middle finger are each pointing in separate directions. If that method works for you, then by all means use it. But for me, I found that method hard to memorize. I was never sure which finger was supposed to point where, but with the method I'm about to show you, I think it's a little easier. For a rotating body, you simply curl your fingers so that they rotate in the same direction. Stick out your thumb, and your thumb will point in the direction of the rotation vector. This is what's shown in this picture here. As for the cross product, which might look something like x cross y equals z, I imagine myself pointing my hand directly towards x, the first vector, and then curling my fingers towards y, the second vector. Once that's done, your extended thumb will again point in the direction of z, the third vector. I also made this little animation to illustrate centripetal acceleration. You can see how the centripetal acceleration always points towards the center of the circle, otherwise known as the instant center of rotation. The formula for the magnitude of centripetal acceleration is v squared over rho, where rho is the instantaneous path radius. Sometimes, though, the path isn't a perfect circle. As we'll see in some of the questions, the path radius can continuously change, but for centripetal acceleration, all we need to know is the path radius at that very instant, hence the instant center of rotation. Now for problem 1. It states, the automobile is originally at rest at s equals 0. If its speed is increased by dv dt equals bt squared, determine the magnitudes of its velocity and acceleration when t equals t1. I've represented the car with a dot, and I've also drawn out the path to scale based on the dimensions from the problem. For this question, we measure the position s as how far the car is along the path. The question gives us an expression for the rate of change of speed, which is the same thing as tangential acceleration. We can integrate that to get a function for the speed, and integrate again to get an expression for the position. Note the constants of integration. If you remember from the previous week, I said that you can usually find the constants of integration from the initial conditions. The question tells us that the car is originally at rest at s equals 0. So if we substitute in that information, then we find that all the constants of integration are 0. Next, let's figure out where the car is at time t1. If we substitute in 18 seconds, we find that s is equal to 131.22 meters. Since the straight part of the path is only 100 meters, that means the car is on the curved part of the path. The first part of the question is asking for the magnitude of velocity. We simply plug t1 into our speed function and find that the magnitude of velocity is 29.16 meters per second. The second part of the problem asks for the magnitude of acceleration. Since the car is on the curved part of the path, there are two components of acceleration, tangential and centripetal. We can find the tangential part using the acceleration function that we already have, and it comes out to 4.86 meters per second squared. As for the centripetal component, it's straightforward to use the formula for centripetal acceleration that I showed earlier to find that the centripetal acceleration is 10.629 meters per second squared. We combine the two acceleration components, and we find that the total acceleration magnitude is 11.687 meters per second squared. Problem 2 states, the particle travels with a constant speed v along the curve. Determine the particle's acceleration when it is located at point x equals x1. The first thing that we want to do is find the direction of travel at x1. I've drawn the tangent line here in red. We can find the slope of that tangent line by using the derivative of y with respect to x and substituting in x1. You can convert a slope to an angle by using the inverse tangent function, and we find that the angle of the tangent line is negative 26.6 degrees. The reason we need to do that is because the center of instantaneous rotation is always perpendicular to the tangent line. In this case, we don't know the radius of curvature, but we can find it using this formula. The formula asks for the second derivative of y with respect to x, so we can find that function as 2k over x cubed. Substituting in x1 into these functions tells us the magnitude of a centripetal acceleration, which is 322 millimeters per second squared. We can break that into x and y components by using cos and sine functions respectively. Remember that for the angle, we need to add pi over 2, since the centripetal acceleration is perpendicular to the tangent line. Because the particle's speed is constant, there's no tangential acceleration. Problem 3 states, the slotted link is pinned at O, and as a result of the constant angular velocity theta dot, it drives the peg P for a short distance along the spiral guide r equals a theta, where theta is in radians. Determine the velocity and acceleration of the particle at the instant it leaves the slot in the link, i.e., when r is equal to b. Here's my reconstruction of the problem to scale. The slotted link rotates at a constant rate until it reaches this point, where the peg exits the slot. At this point, r, which is the distance from the origin to the peg, equals b, which is the length of the slotted link. This means we can substitute b in for r in the expression for the spiral guide, which tells us that the peg exits when theta equals b over a. In this problem, it's helpful to use cylindrical coordinates. That means that instead of horizontal and vertical components, we use radial and angular components. The radial component is the direction outward from the origin, and the angular component is the direction rotating around the origin. Using these coordinates, the radial velocity is simply r dot, which is the derivative of r with respect to time. Since we know r equals a times theta, we can take the time derivative to find that the radial velocity is a times theta dot. Substituting in a and theta dot gives us a value of 1.2 meters per second. As for the angular velocity, its formula is r times theta dot. So we plug in values and find that it is 1.5 meters per second. Combining the two components results in a total velocity magnitude of 1.92 meters per second, which is the answer to the first part of the problem. Now we can move on to acceleration. The formula for radial acceleration is r double dot minus r times theta dot squared. R dot is just a constant as we found earlier, so r double dot is 0. Substituting in the remaining values gives a radial acceleration of negative 4.5 meters per second squared. The formula for angular acceleration is r times theta double dot plus 2 times r dot times theta dot. Theta double dot is just 0 since the link rotates at a constant speed. We know all the other values already, and plugging them in gives us a result of 7.2 meters per second squared. Combine the two components, and we find that the magnitude of acceleration is 8.49 meters per second squared. So that's it for today's video. As always, you can contact me at this email address if you have any comments or questions. So thanks for watching, and I'll see you in the next video.